For the last module in this chapter, we're going to start looking at phase changes, calculations with phase changes, delta H or heat of vaporization, fusion, etc. What's involved when we change phase? How much heat goes into a phase change? How much heat needs to be released to undergo a different type of phase change? When is your heat exothermic? When is it endothermic in relation to phase changes? And all of that. So you do need to know the names of the various phase changes: fusion, freezing, vaporization, condensation, sublimation, deposition. For a given phase change, be able to tell me if the enthalpy increases or decreases, therefore, is it endo or exothermic? You do need to understand heat of fusion, heat of vaporization, understand heating and cooling curves, be able to calculate the heat involved in phase changes, understand what phase diagrams represent. You're going to use the Clausius-Clapeyron equation to determine some information as well, and be able to explain unusual properties of water as a result of your intermolecular attractive forces. So the phase changes themselves. Evaporation is when the liquid goes to a vapor at any temperature. Vaporization, the liquid to the gas at boiling point. So it's kind of hard to think about it that way, but like liquids can evaporate. You know, if I put a glass of water out on the countertop, it will eventually all disappear. It will evaporate away. If I increase the temperature, it will evaporate faster, yes, but it's because water has a vapor pressure. It doesn't have to reach its boiling point to actually evaporate. So liquid going to a vapor at any temperature is evaporation. The liquid going to a gas at its boiling point is vaporization. Condensation is when the gas is condensed. The gas goes to a liquid at its boiling point or its condensation point. So it condenses and vaporizes at the same temperature. It's just, which direction am I going? Am I going from a liquid to a gas or from a gas to a liquid? So pure substances will boil and condense at the same temperature. They will also melt and freeze at the same temperature. This really kind of throws students off when they think about it, but I want you to think about water. We know water, if it's at 100 degrees C, it's going to boil. But what if I have water vapor and I bring it to 100 degrees C and then I cool it down just a little bit more? It's going to condense. If I have water at 0 degrees C, 0 degrees C is where water freezes, right? But it's also where it melts. It's an equilibrium state. You will learn about equilibrium in a different chapter, a different section in Gen Chem 2 specifically, but this is at the point where the system can go either direction. It could freeze or it could melt, and it happens at the exact same temperature. Your boiling point, again, remember from the previous module, the boiling point is the temperature where the vapor pressure is equal to your atmospheric pressure. So we have what we call normal boiling point. The temperature with the vapor pressure is equals your standard atmospheric pressure, which is 1 atmosphere or 760 torr, 760 millimeters of mercury. But that doesn't mean it has to boil at that temperature. It does depend on the altitude you're at and the atmospheric pressure around you. Fusion is just another word for melting. Imagine things fusing together. They're coming together. Melting, same thing. Solid going to a liquid. Solidification, crystallization, or freezing is when your liquid goes to a solid phase. Your melting point and freezing point is the temperature at which the vapor pressures of the solid and liquid are equal. Sublimation is when you go from a solid to a gas phase, straight from solid to gas, that is possible. And deposition is when you go straight from a gas phase to a solid phase. So just looking at them a little bit drawn out with enthalpy involved with it. So enthalpy, again, your heat of reaction. You do need to know the names of these phase changes and whether or not these are endo or exothermic. So if the temperature is, if it's going up, you see the arrows going up, this takes heat. It takes heat to go from a solid to a liquid phase. It takes heat to go from a liquid to a gas phase. Those are endothermic. If I am condensing, freezing, depositing, those are exothermic because I'm going to remove heat to do that. Your delta H vaporization or heat of vaporization is the enthalpy change when 1 mole of a pure liquid is vaporized. How much heat did it take to vaporize that sample? Delta H of fusion or heat of fusion is the enthalpy change when 1 mole of a solid pure substance, when 1 mole of a pure solid melts. How much heat was involved to melt it? So again, you do need to know these terms here. You need to recognize when they're what phase change they represent, and you need to know if they're endo or exothermic. You also need to understand delta H vaporization and delta H of fusion. So vaporization, 1 mole of a pure liquid being vaporized. Delta H of fusion, 1 mole of a pure solid being melted. So again, we say the crystals melt, they fuse together when they melt, so that's kind of where the word fusion comes from. 2 points I want you guys to think about. In general, the stronger the IMFs, the higher your delta H and delta H vaporization, delta H of fusion. Because if we have stronger IMFs, it's holding these compounds together, it's going to take more energy to break them apart and break them away from each other. Remember, ideally speaking, in the gas phase, if a gas is behaving in an ideal fashion, it doesn't have any interaction with any other gas particles around. So if I'm trying to go to a full gas phase, I'm trying to break apart all intermolecular forces, all things holding these together. They form intermolecular forces for energy stabilization. But if I'm trying to completely destroy all of that or break all that apart so that these particles can float around freely without interaction of one another, it's going to take more energy if they have higher IMFs. Second is for a given substance, which is generally greater, delta H vaporization or delta H of fusion. And what do you think? Why? Well, the answer here is your delta H vaporization is generally higher. Is it always higher? We can always find exceptions, but generally speaking, delta H vaporization will be higher. Remember, vaporization requires that the IMFs be completely overcome. You're going to a gas phase. So fusion, going solid to liquid phase, we do have to overcome some of the IMFs, yes. Liquids have a fixed volume, but no fixed shape because they can slide past each other, but they still have those IMFs present. Vaporization is when you're going from a liquid to gas phase. Vaporization requires the IMFs to be completely overcome. Remember, gases have no definite shape or volume. And if they're ideal, we assume they have no attractive force to one another. So it's going to take more energy. Delta H vaporization is usually going to be higher because we're completely breaking apart all IMFs at that point. We also want to talk about the Clausius-Clapeyron equation. This is a relationship between delta H vaporization and your vapor pressure. If we plot the natural log of pressure versus 1 over temperature, this gives us a straight line where the slope is delta H vaporization over R being your gas constant. As chemists, we like this equation because it gives me this. Natural log of pressure is equal to negative delta H over R times 1 over T. This takes on the form y equals mx plus b, where we see we don't care much about what that intercept is, to be honest. The intercept isn't helping us here. We really want that slope. But chemists like linear equations. We like things that we can plug in, make them simple math problems so that we can just go ahead and use them. From this, I can plot a series of vapor pressures, the natural log of a series of vapor pressures, at a series of temperatures, corresponding temperatures, and I can actually calculate my delta H vaporization here. And I can use that information for further calculations. So the unit of R is joules per mole K, so delta H vaporization will have joules per mole for units here. Be careful. We usually represent delta H with kilojoules just because it tends to be a larger number. If you get it from this graph, it will be in joules per mole. Be careful with that. How can I use this information though? Well, let's look at the Clausius-Clapeyron plot for dichloromethane. We get a plot here where y equals negative 3773x plus 18.8. So our equation here, sorry, I keep hitting my screen. Here is our equation. Determine the delta H vaporization of dichloromethane given the vapor pressure and versus temperature data. Well, I know my slope is equal to negative delta H vaporization over R. So I can go ahead and plug that information in. I get my slope from the plot itself. I know my value of R, 8.314 joules per mole K. I can then just simply solve for delta H vaporization. We find delta H vaporization, 3.14 times 10 to the 4th joules per mole, which I convert to 31.4 kilojoules per mole. I can then use this information for another calculation. So it's a great way for me to get the piece of information I need to use for another calculation. So you determine the slope of the line graph by plotting the natural log of vapor pressure versus 1 over temperature in Kelvin specifically. So if you're practicing any of these problems in your book, make sure you're plotting it this way. The vapor pressure is a function of your temperature. So that means that the natural log of vapor pressure goes on your y-axis, function of, and 1 over temperature goes, see temperature Kelvin to the -1, that means 1 divided by temperature goes on your x-axis. You determine that slope and you can then use that information for another calculation. Another way we can use this equation is the 2.4. You will be given this equation if you're asked to use it on a quiz or exam. I do not expect you to memorize this specific equation. But just 2 measurements of vapor pressure and temperature are needed to use this equation. Fewer data points won't give us as accurate of an average because there's less averaging out of the errors, but we can still use it. You're going to use this to predict your vapor pressure. So if you know the heat of vaporization and the normal boiling point, then you can figure out the rest of the information you need. So remember, vapor pressure at the normal boiling point, 760 torr or 1 atmosphere specifically. But we will use this to actually predict our vapor pressure. As an example, calculate the vapor pressure of methanol at 12 degrees C. Vapor pressure is temperature dependent. So remember what vapor pressure is. Vapor pressure is basically I have some kind of system. I have a liquid inside. Let's say this is a closed container. And I know that some of these particles are going to go to the gas phase, while some stay in the liquid phase. The vapor pressure is the pressure of these particles above the system that pushes onto here. And it's dependent upon temperature, it's dependent upon the system you have, etc. But how much pressure is that vapor pushing on that liquid below? It's temperature dependent because as I increase the temperature of a system, then those particles should be able to escape more easily from the solution. I want to know the vapor pressure of methanol specifically at 12 degrees C. So we're going to use our Clausius-Clapeyron equation. So we see our equation here. Natural log P2 over P1 equals negative delta H vaporization over R times 1 over T2 minus 1 over T1. T1 is our boiling point, 64.6 degrees C or 337.8 K at 760 torr. This is my normal boiling point. Do I expect you to know that? No. I would give you that piece of information if you needed to do this exact calculation. The second temperature is 12 degrees C, or 285.2 Kelvin. I want to know what the vapor pressure is at this temperature. And I'm told that my delta H vaporization is 35.2 kilojoules per mole. So I'm just going to plug in everything I know. I know delta H vaporization. R is a gas constant. My second temperature, 12 degrees C, but in Kelvin. My first temperature is my actual boiling point of methanol, but in Kelvin. Plug it all in. We know that my first pressure is 760 torr because I am looking for the pressure. That's my pressure at boiling point. That's my normal boiling point, 64.6 degrees C or 337.8 K. And I'm just solving for P2 here. So do the calculation, isolate P2, and we see that P2 is equal to 75.4 torr. What that means is the vapor pressure of methanol at 12 degrees C is 75.4 torr. Another thing we want to look at is energetics of phase changes, so heating and cooling curves. When you're doing a calculation like this, I highly recommend you draw out some kind of curve that looks like this to be able to visualize what's happening. When you're looking at a heating and cooling curve, these slanted lines, such as these, slanted lines represent temperature changing. So that's when we've done, like in the thermodynamics chapter, where we talked about, how much heat is evolved or required if the temperature moves from 30 degrees to 50 degrees. That's where we use the Q equals MC delta T equation. That is your kinetic energy increasing. Horizontal lines, like this, are where your temperature is constant. You're undergoing a phase change. That's your potential energy increasing. So that's an actual phase change. The potential energy difference between the liquid and gas is greater than the potential energy difference between the solid and liquid. When drawing them, do not pass the melting point or boiling point without stopping to allow a full phase change. This is kind of going back to that delta H vaporization versus delta H fusion. Do not forget to stop for boiling points. Melting points, though, someone will, and you will get the wrong answer. We're going to do a few examples, but you have to consider that. You have to keep track of those. Phase change curves, heating or cooling. You need to be able to label when the kinetic energy and potential energy is changing. So remember, phase changes our potential energy, temperature increases our kinetic energy. Be able to locate your melting point or freezing point, same temperature, melting and freezing occur at the same point, boiling point, be able to label what phases are present at any given point. So, enthalpy of vaporization. For water, is 40.7 kilojoules per mole. That means it takes 40.7 kilojoules to take 1 mole of water from liquid to gas phase. The enthalpy of condensation is opposite of that. This is going from a liquid to a gas phase. Opposite side would be going from gas to liquid. It's endothermic to go from a liquid to a gas phase. It's going to take energy to do so. If I instead want to bring that gas down to a liquid phase, the value is the same. The sign changes because remember, enthalpy is a state function. It's going to be the opposite sign. Delta H of vaporization, endothermic. Delta H of condensation, exothermic. Why are steam burns so much more harmful than being burned by boiling water at the same temperature? Because a steam burn is trying to release all of that energy. This is delta H vaporization for water specifically, 40.7 kilojoules per mole. 1 mole of water is only 18 grams. It's not very much. That's a lot of heat. A steam burn is trying to release all that heat. So it's releasing it onto your skin when you're getting a steam burn. One of my best friends works in a kitchen, and she's gotten some pretty severe burns this way. That's why those steam burns are worse than just boiling water, because the steam keeps burning and has to release all that energy to be able to condense on you, unfortunately. Enthalpy of fusion. Fusion again, going from a solid phase to a liquid phase, is 6.02 kilojoules per mole for water. The enthalpy of crystallization or solidification, this means going from a liquid to a solid state, is negative 6.02 kilojoules per mole. So again, if I'm going from a solid to a liquid state, that's exothermic. Solid state to a liquid state is endothermic. It takes energy to do so. I need to put in enough energy to allow those IMFs to start sliding past each other. But a liquid to a solid state is exothermic. I need to remove that energy so those particles can come back together and lock into that solid structure. You don't need to memorize values of the enthalpies for the phase changes. I will provide those. If you're doing homework in your book or on Chem 101, you can look them up. But if you on any quiz or exam, I will give you those values. So, to be able to calculate phase changes, or enthalpy changes in general, draw the heating cooling curve first. Do this first, please. If you do nothing else, draw this curve first. Use Hess's law. Hess's law allows us to add up all of the given enthalpy changes. Make sure you're keeping the signs correct and the units consistent. We're going to do these calculations, and sometimes you're going to see that the units are going to give you joules. Sometimes they're going to give you kilojoules. You've got to make sure you're aware of which is which. For temperature change portions, use specific heat, mass of substance, and degrees change. So the MCAT equation. Remember, this is your kinetic energy. For phase change portions, use the given enthalpies and moles of a substance, and we're going to do stoichiometry. This is your potential energy changing. This is your phase change. For heating curves, all values will be positive because it's an endothermic process, and for cooling curves, all values will be negative because it's exothermic. If I'm heating something up, I'm putting heat into the system. Therefore, it must be positive. If I'm cooling something down, I'm taking heat away from the system, so it's exothermic. To give you a quick view before we actually do one, what it looks like, I'll draw a heating curve first, then a cooling curve. Let's just say water. And we'll say 0.00 degrees C, 100 degrees C. We start out low. It starts heating up. We undergo a phase change. We heat up to 100 degrees. We have another phase change, and then we can keep heating. This is a solid phase here, liquid phase, and a gas phase. This is my liquid to gas transition, so delta H vaporization. This is my solid to liquid, so delta H effusion. Let's see, this is temp changing. So my kinetic energy is increasing. Same here. Same here. And here, under my two phase changes, the temp is constant. So my potential energy is increasing. This would be a heating curve. If I had heat being removed, it would look opposite of this. We see our potential energy during our phase changes. And it's not as pronounced because I had to draw it smaller, but our kinetic energy changes here as it cools. This is endothermic. So all values positive. This is exothermic. So all values will be negative. Okay, how much heat is required to convert 50 grams of ice at negative 12 degrees C to liquid water at 24 degrees C? Specific heat of liquid water is 4.18 joules per gram degree C. The specific heat of ice is 2.09 joules per gram degree C. Remember, those are phase specific. And the delta H of fusion is 6.02 kilojoules per mole. And I know I have all the work written out here, but let's describe how we would write this out if we had to do it ourselves. So we see here that we want to convert 50 grams of ice, that's at negative 12 degrees C, to 24 degrees C. So I'm going to draw, this should actually say negative 12. I'm going to draw a curve from negative 12 degrees C up to 0 degrees C because I need to undergo a phase change at 0 degrees C. I'm going to draw a second one at 0 degrees C for my phase change. Once I get through that phase change, I'm then going to keep heating that sample up until I reach 24 degrees C. So another increase in kinetic energy. For increases in kinetic energy, I'm going to use my MCAT equation. And for phase changes, I'm going to use what I call stoichiometry. So I'm going to call this Q1, I'm going to call this Q3, and I'm going to call this Q2. Q1 is heating up 50 grams of ice from negative 12 degrees C to 0 degrees C, because I have to undergo a phase change at 0 degrees C. The specific heat of ice is 2.09 joules per gram degree C. So that's where I see I've got 50 grams of water, solid phase, times the specific heat of ice, times my change in temperature, 0 degrees C minus negative 12 degrees C. It gives me 1254 joules. And I've underlined my sig figs there. Grams have canceled, degrees C have canceled, and I'm left with joules. Q2, I'm doing stoichiometry. I've got 50 grams of ice that needs to be moved to water. How many moles of water is that? Convert to moles. Now, I know that my delta H of fusion is 6.02 kilojoules per mole. I know it takes 6.02 kilojoules to heat up 1 mole of water. So I've got this in moles now. Now I can cancel my moles, calculate kilojoules, and I get 16.7 kilojoules for heat for the phase change. Then Q3, I've got 50 grams of water again. This time it's actually liquid phase. Too much copying and pasting. I'm going to use now the specific heat of water, not ice, 4.18 joules per gram degree C. And I'm heating this up to 24 degrees C, so 24 minus 0 degrees C gives me 5,016 joules, underline my sig figs. But note, joules, kilojoules, and joules. You got to be careful here. Add them all up, Q1 plus Q2 plus Q3. This is an application of Hess's law. 1,254 joules with 3 sig figs. That gives me 1.25 kilojoules. 16.7 kilojoules. 5,016, but I need 3 sig figs, so 5.02 kilojoules. Add all of those up, and I find my final answer to be 23.0 kilojoules. So it will require 23.0 kilojoules to heat up 50 grams of ice from negative 12 degrees C to 24 degrees C. How much energy does it take to convert 0.5 kilograms of ice at negative 20 degrees C to steam at 250 degrees C? I give you the specific heat of ice, specific heat of liquid water, specific heat of steam, delta H of fusion, and delta H vaporization. This is actually worked out in the additional practice video if you'd like to see it there. But otherwise, if you add it up, the answer is 1680 kilojoules. So I want you to go ahead and work on this on your own, or if you want to see the key, it is under the additional practice as well. Okay, heating curves of water. So what's actually going on here? Well, below 0 degrees C, here below, we got below 0 degrees C here. We've got ice. Now, people don't think about this a lot, but I can keep cooling water. As long as it's below 0 degrees C, it's ice, but that doesn't mean I can't make it colder and colder and colder. It's just still going to stay ice. It's not going to do a phase change. It's going to stay cold. It's kind of like how water can be a liquid phase anytime between just above 0 degrees C and just below 100 degrees C. It can be cold water, it can be room temperature water, it can be hot water, but it's still water. So the first thing we've got here, step 1, is our ice is warming. As the ice starts to warm up, we're giving that ice more energy. The intermolecular forces aren't as important because now we're adding energy to the system. It's starting to kind of moving around more, getting a little more disrupted in its IMFs, its crystal structure, etc. I then melt the sample. So here we see ice is melting to a liquid phase. Delta H of fusion, 6.02 kilojoules per mole. Keep going. I'm going to heat up that water. So this whole time, 0.3, I've got water. But again, do I have cold water? Do I have room temperature water? Do I have hot water? It's still water. The liquid water is warming. Number 4, I'm going to undergo a phase change again. The liquid water being vaporized to steam. This takes 40.7 kilojoules per mole, an exorbitant amount compared to bringing ice to a liquid. And we see here drawn to scale the amount of heat added. So a little bit added to melt it, but a large amount is being added to vaporize this liquid. But remember, water has hydrogen bonds. Hydrogen bonds are the not the strongest. Ion dipole is the strongest, but they're a very strong intermolecular force, and they're the strongest you're really going to have with a covalent type bond. They're a specialized dipole, and they're stronger than an average dipole bond. It's going to take a ton of energy to break that apart. Once we finally do, we get them onto the vapor phase, then we can keep heating up that water. So the steam being warmed up even farther. And again, the steam could go, as long as it's above a little bit above 100 degrees, it's going to be steam. It can keep heating up from there as well. So this is basically what's happening. The next thing I want to look at is phase diagrams. But in order to understand phase diagrams, we need to first understand some terminology. So we've got different types of curves here. We've got different points, temperatures, pressures, etc. So a fusion curve. A fusion curve is the transition you find between your liquid and solid states. So imagine things are melting, they're fusing together. The fusion curve is liquid to solid, solid to liquid. That point is called the fusion curve. Yes, fusion is considered to be melting, but it's still the point between the two. What I mean by that is, like, if I look at water, 0 degrees C, I'm at this point. If I go right below here, I'm going to form a solid. If I go right above here, I'm going to form a liquid. The curve itself is called a fusion curve. The sublimation curve is the transition from solid to gas phase without passing through an intermediate liquid phase. This one kind of throws students off because they think, how can you go straight from solid to a gas phase? You can. You could go straight from solid to gas to solid. It's pretty cool to watch. It's kind of a nice experiment you can do. You can pull caffeine straight out of coffee this way. It's a purification technique, actually. And you can heat up coffee and sublimate it straight into caffeine and find purified caffeine crystals that way. It's a cool experiment we've done with students before. But going straight from solid to gas phase without passing through your intermediate liquid phase. Vaporization curve is just your transition between your gas and liquid states. So to vaporize something is to go from the liquid to gas state, yes. But remember, they're happening at the same point. So we call the curve the vaporization curve. The triple point is the point on a phase diagram at which all three states of matter, solid, liquid, and gas, coexist. It's kind of cool to see a triple point. I recommend looking this up just on Google because why not? But you'll see a sample boil, freeze, and melt at the exact same time. Exact same temperature, exact same pressure. It will boil, freeze, and melt all together at the same time, just repeatedly. It's really kind of cool to watch. Critical point is the point on a phase diagram at which the substance is indistinguishable between your liquid and gaseous phases. Critical temperature, the temperature above which it's impossible to liquefy a gas. Critical pressure, the pressure required to liquefy a gas at your critical temperature. And supercritical fluid is a substance with both gas and liquid-like properties. And so for supercritical fluid, it's neither a liquid nor a gas, but it does possess properties somewhat intermediate between the two. The substance is at temperatures and pressures beyond its critical point. So it's not a liquid, it's not a gas, but it's kind of an intermediate in between them. Supercritical fluids are really important. A lot of application for there. For example, they used to use, I believe it was carbon tetrachloride, to pull caffeine out of coffee. But even though it would all evaporate away, carbon tetrachloride is a carcinogen. And so people got very concerned about the health effects of it. Even though we could promise that it wasn't in there anymore, people were understandably concerned. But now they use supercritical CO2, carbon dioxide, to actually pull the caffeine out of coffee, which I think is kind of cool. So some real world application there. Here's what a phase diagram looks like. So you need to be able to identify the following regions: your fusion curve, sublimation curve, vaporization curve, triple point, critical temperature, critical pressure, and supercritical fluid. We see here, you've got your temperature on your x-axis, your pressure on your y-axis, and as I increase temperature, I'm going from solid, liquid, gas phase. No surprise, right? Increasing the temperature, I'm giving these particles more energy. They're going to move around a lot more. Pressure, as I increase the pressure, I can go from first gas to solid. That shouldn't surprise you either. As you're increasing the pressure, you're putting those particles closer together. They're going to feel those attractive forces more likely to form a solid phase. But at increased pressure, but also increased temperature, you're going to form that liquid. A point on the line. So the line itself, here you can see a difference in color. That's the lines. A point on a line itself represents two phases existing in equilibrium. So if I drew a point right here, this would be something existing between a liquid and a gas phase. Right here, between a solid and a liquid phase. We see here we've got our sublimation curve. Sublimation going between solid and gas phase. We've got our, so any point here between a liquid and gas phase, it's your vaporization curve. Any point here on this line between your solid and liquid is your fusion curve. So any point in there is your fusion curve. Let's see. Your triple point is where all three come together. So that's where they're all three in a touch. Critical point and critical temperature. Critical pressure, supercritical fluid will be up here. So I need you guys to be able to identify all the parts on here and be able to look at these and be able to draw them, be able to understand them, and be able to see what's really happening here. Be able to, if I give you a point on a curve, tell me what transitions are happening or what states are you in between. Another thing to think about, though, is that sometimes you're going to see fusion curves with a positive curve and some will hit the negative or slope. What I mean by that is this curve right here. Let me draw this so you can see it. I clearly cannot draw a straight line to save my life. These two curves. So when is the fusion curve expected to have a positive curve? Or a negative, or slope? And why do I see CO2 and water having different points? Well, when you have a positive slope, such as in CO2, this is most common. And the reason this happens is the solid phase is more dense than the liquid phase. So most species will have this positive curve. CO2 looks, I know the way I drew it was very straight. It is slightly positive there, sorry. Slightly positive. But you'll see that positive curve when your solid phase is more dense than your liquid phase. So your liquid phase will float on top if you're compared to the solid phase. We see this negative slope with things like water so we see this for water. And this happens when your solid phase is less dense than your liquid phase. So if you see a sample like this, you know that the solid phase is going to be floating on top of that liquid. And we've already talked about in Enthalpy Module why that's important for water, why that happens. Remember, that's due to your intermolecular forces. When water forms that solid phase, it needs to maximize that space to keep its hydrogen bonds in play. And to be able to do so, it creates kind of a void or a pocket in the structure itself that makes ice less dense than water. And for a quick example, what phases are present at point F on the phase diagram? Point F, if I look right here, do I remember what this means? Well, how do I fill these out? My gas, my solid, my liquid. This is going to be my critical pressure. This is going to be my triple point. So if I was to look here, I'm on point F. I'm going between a gas and a liquid phase. So between your gas and your liquid. I could ask you things like, I'm traveling this way. What am I doing here? What phase change am I undergoing? What is this point here? What am I doing here? What if I went all the way through to here? What am I doing? What phases am I passing through? So you should be able to identify the phase diagram, label the phase diagrams, and be able to understand and use the phase diagrams. Also, is this a positive or a negative slope? What do you guys think? Is this sample more or less dense in its solid phase compared to its liquid phase?